So we got a couple more presentations left for the Data Palooza today. Next up is Anya Supati, and she is actually a data analyst in the Sales and Distribution Analytics team. It's actually the same team Rohan works for, right? You guys are on the same team?
Yes.
Okay, and he gave the first presentation today. So they're doing a lot of great work over there. She's been there for a little over a year, and she said her favorite band is Van Halen. So, good taste there. Rock on. One side note, for those of you that might be interested, there is one piece of cake there. Just one. We could have an arm wrestling competition, but I feel like that... No, I'm just kidding. So anyways, whoever wants a piece of cake, please take it. If it's not gone in the next 10 minutes, maybe I'll take it. I don't know. But we need to have that be consumed. So please take that piece of cake if you're hungry. All right, enough of that. Anya, please welcome Anya to the floor.
Okay, hello everyone. How do I sound? Okay. All right. Today I will talk about the experimental design, but I'll be mainly focusing on the principles, not really on the data. And the data also scenarios that I use for the presentation are also fictitious, so don't worry. Many of you probably already wonder, what is an experimental design? Simply put, it's just a plan for running an experiment. As we go along, it might seem to some of you that my examples are far from most of you think of when imagining marketing campaign. But the reason for my examples is just to simply stress on the principles of the design itself first. So what does the experimental design actually measure? It simply measures the response to the treatment. And in experimental design, we refer to treatment as Y. And that's how we are going to be denoting the response in our presentation. So what are the factors that are used in that design? There are certain factors that we would like to study, and we want to study their impact. Suppose I have 2 hair conditioners, and I would like to study which is better. So these would be my factors. There are also other factors that we think of, but we really don't want to consider them in the model since they have little or no impact on the design, on the response. Let's say me liking brand 1 over brand 2 doesn't really impact the performance of the conditioner itself. There are also other factors that may impact the response, but we don't really want to study them. We will control them by holding constant. Let's say washing hair in a different water temperature will definitely impact the response, the performance of the conditioner, but we don't want to really worry about the water temperature as an extra factor in the design. We will then hold that water temperature as constant and run our experiment just using same water temperature. There are also other factors that we think have effect on the response, but for some reason we cannot hold them constant. Therefore, we can block on those factors. These are called blocking factors. All right, so let's build an experimental scenario, just imaginary scenario. Suppose that the gas station owner around here asks me to run an experiment for him. Let's say he really wonders about various gas additives that he sells in his little shop. He knows that some brands sell better, some brands don't really sell that well. He also wonders, is there a true difference between one brand and another? He also saw this article online that says, in-store gas additives, more MPG or no difference. All right. Me and the gas station owner would sit down together and we'll think out the hypothesis. The hypothesis would be, we would like to know if different types of gas additives result in similar miles per gallon increase. That sounds like a fair hypothesis, right? All right. Then he gives me 4 of his brands that he wants me to test. And in my design, I would have just one treatment at 4 levels, and I would know them as L1, L2, L3, and L4. All right. So my question is, how am I going to find a lot of cars at the same place where I can treat them all with various gas additives? Don't worry, I did not go around progressive parking lot applying gas additives to your cars at random. I did not do that. But just for the simplicity of this experiment, let's divide a parking lot into 4 quadrants. And since these cars arrived at the parking lot at random time, and they come from all the same parking lot, we think that our experimental limits, which are cars, are homogeneous. They're all uniform. They're very similar. Therefore, we will divide the parking lot into 4 quadrants, and this is actually very important. The quadrant number 1 would get just one treatment level. Let's say we'll just apply just treatment L1 to these cars. At random, we'll pick some amount of cars. Then quadrant number 2 will receive just treatment level 2, and we'll at random pick some amount of cars. And same thing we'll do to the remaining quadrants. We're doing this because we think that those cars arrived at random and they are alike. That's why we're doing this. All right. So probably you have heard something like experimental run. Experimental run is simply a collection of the value of the response variable, so it's just one observation. Since we have 4 quadrants and 4 levels of a treatment, the minimum amount of runs is 16. So just to make it really simple, we'll just test on 16 cars. All right. So based on my assumption, the most appropriate design for this experiment is completely randomized design, which is also referred to as CRD. There are several principles of CRD. The first one is randomization. You probably wonder, how am I supposed to do that in my data? How am I supposed to randomly assign treatments to my subjects in the data? You can do it simply by writing a simple SAS code that will randomly generate numbers from uniform distribution, let's say from 1 to 100, and add it to your data. And if you sort your data by that random number, what it will do, let's say this is our parking lot quadrant. And parking lot quadrant is assigned as 1, and 2, and 3 data is cut off. And treatment level for parking lot quadrant number 1 will be just at level 1. And for quadrant 2, we'll just use level 2. And the car numbers are randomly shuffled thanks to this random principle. We can also write this in Excel. The same formula would work in Excel, or however you want to do it, either SAS or Excel. Then our car numbers will be shuffled and assigned at random to parking lot quadrant and the treatment. All right, so after I have collected the results and studied the performance of the gas additives, what can I do now? I can actually conduct analysis of variance to determine whether there are differences between the types of gas additives. And the model will be really simple. It will be just a linear model with one term in the model, with just treatment, some error term. And again, our hypothesis would be that all the treatments are the same. There's no difference. And we are actually hoping to reject that hypothesis while performing the analysis. Your alternate hypothesis would be that at least one of the treatments is different. And this is what we're hoping to find out for our gas station owner. All right, so how about I plot the response variable by treatment? And these are my treatment levels, treatment 1, 2, 3, and 4. What I immediately see is that there's a huge variation of the response. What? Something happened? All right. What I immediately see is that there is a huge response of the variation for each of the treatment levels. So let's imagine that each of the dots is a response, the increase in miles per gallon for each of the cars. So why are they so widely spread? Why there's so much variation? Can we detect the differences in treatments from this design? So let's imagine that this dot is a low-performing car, and this dot is a high-performing car. So basically, if you apply same treatment to two different cars, they will definitely react differently, right? The response will be different. Low-performing cars will react differently. High-performing cars will react differently. All right. So what happens here is that we have a problem. It's really hard to determine if the treatments are different due to the random variation. That comes from somewhere else. That comes from our experimental units. The experimental units have our extra source of variation in our model that we are not accounting for. So we can also view the rest of the results. We can view the mean response for each of the treatment levels. Although the treatment at level 4 has the highest mean, the test does not show the model is significant. The p-value is much higher than alpha, which is 5%. Therefore, we fail to reject null hypothesis, and we don't have enough evidence to conclude that at least one of the treatments is different. All right, so what happened? What actually happened to our design? Was it a really good idea to ignore car types? We did think that maybe there are some cars with higher or lower performance that we use for our design. But in the beginning of the experiment, we did assume that we would have cars that are homogeneous, that are all alike. Because they came from all the same parking lot, we took them at random, and we assumed that they are all alike. But in fact, they were not. Suppose that the subject matter expert comes to us and says that he determined that cars are actually very different. They are, in fact, very different from each other. And even he selected at random from the same parking lot. How about we identify that cars in our experiment were low performance, high performance, average performance. In order to isolate the variability due to the differences among cars, we would choose to use car types as a blocking factor. And that takes me back to the very first definition we looked at today that said that there are some factors that probably impact the response, but we, for some reason, cannot hold them constant. We cannot have all 100 hammers for our experiment. Therefore, we would block them. We would use a car type as a blocking factor in our design. So based on my assumptions, the most appropriate design is randomized block design, which is also called RCBD. Now, there is actually a very important principle that tells blocking restricts randomization. Before, we had 4 quadrants of the parking lot, and we assigned to each of the quadrants just one gas type. Now, instead of quadrants, we take blocks. We take grouped cars into blocks, and we assign to each block all possible treatments. So this car type would get all the treatments. This car type would get all possible treatments. So can we go back? So here, this column is denoted as 1 for block, and first block would get all the treatments, and they would be also assigned at random. So we would take cars at random and assign all the treatments to those cars. What I can do next is view the linear model again and run some plots for response by block this time. And what I see immediately is that actually the response variation has shrinked. It actually went down. We don't see this huge spread in the data. In fact, if you look closely here, the block number 2 has only 3 data points instead of 4. What that means is those 2 cars gave the same exact response. So it works. We did manage to reduce the variability that comes from experimental units. And looking at the model, it definitely, with time, the p-value is significant. So we can determine that there are different, at least one of the treatments is different. Well, now we can look at the terms that we included in the model. Now, instead of only having one term in the model, treatment, we also have block. And they're both significant. What that means that there are significant differences between treatments. And including blocking factor in the model was actually beneficial to analysis. All right, what about which treatment is the best? If the gas owner asks me which of the treatment actually is the best, which of the gas additive is the best, which one should I be promoting more, I can tell that by including in the mean statement Tukey test, and that will allow me to do a multiple comparisons for each of the treatment levels. So treatment level 4 will be compared with all other treatments and stars denote that it's significant. Looking at the means, the treatment level 4 also has the highest mean and is different, statistically different from the remaining ones. And the rest are actually not different one from another. All right, so how about marketing campaign of gas additive number 4? Let's imagine the gas station owner gave me his database with the past purchases of his customers, some external data, some other data that I can use. And he would ask me to find out the best way to promote the product. Let's just step back for now and think of what we just learned so far. We know so far that how to design an experiment to test differences among treatments, and we also know the concept of blocking factor. And these two, can we go back? These are very important things that actually can be applied to planning the marketing campaign, planning the, when there's marketing campaign and brainstorming ideas, what kind of message to send out to our customers, what kind of emails to send, what works best. This actually shows steps how to identify best treatment and how to decide which one is the best and if they are significantly different or not. And the concept of blocking is also very important. If we cannot really take our customers that they are all alike. They are not. The agencies are not all alike. And it's really beneficial to the model to find way to block them on some kind of characteristic so we can control for that extra variability in the model. So traditionally, marketing campaigns are designed in such a way that someone will prepare a predictive model and identify characteristics of customers that are most likely to buy something. Then, using that predictive model, we can take top 20% of our customers and just send them that messages, or hoping that they will respond, that they will buy something. This is how traditionally it's been done. But is it possible that we're only focusing on customers that already decided to buy or not to buy, regardless of the campaign? Let's imagine that there are customers who come to the gas station and they always buy something. They always buy certain type of gas or certain type of gas additive, and whether we send them email with the campaign or not, they will still buy it. There are perhaps customers that will never buy something, and maybe sending them a message will convince them and persuade them to buy something, and that's going to be actual effect of the campaign. But the question is, how can we identify customers that will be positively influenced by campaign? So how about, let's go back to the gas station owner and to his database. Now I have the predictive model that tells me how to identify the best customers. I will take these customers and send them a treatment, which would be maybe a marketing campaign. I will also take customers at random, any customer from the database that were not in the model, and also send them treatment. I will also take the same two groups, model and random, and keep them as a control, meaning I will not treat them with anything. I will not send them anything. What we see here is measurement of model effectiveness. A, B, C, and D could be any continuous values or ratios like increase of sale or maybe response rate. basically here we have treatment and control group, model and random group. If we would like to tell if there's actually a significant difference between model and random, the A minus T should be significant. That means, yes, we succeeded. We did provide our customer with very good predictive model, and model works better than random. If we take control group, the one that did not receive any email, the B minus D should also be significant. That means even though we did not send them any treatment, they still want to buy things we wanted them to buy, and model picked the right customers. But that does not answer the question if the treatment actually worked. In order to find out if treatment actually worked, the difference between A and B and C and D should be also significant. That means not only identifying customers that would have gotten the promotion or bought something with or without our message. That means we are targeting customers that would have not bought something if not for our message, if not for our campaign. And this measurement of model effectiveness is actually borrowed from a true lift model and novel data mining approach that I researched on SAS website. And by maximizing the difference between A and B, C and D, we are hoping to get the true lift. True lift meaning true response that we can definitely tell that treatment really works. That would be it. If there are any questions. Personally, I would be hoping to using this model in my current project. I'm working currently on several marketing campaigns, and I was not able to show my work here since it's not really ready yet. But these are the concepts that I learned and I'm applying in my work. So, any questions? I hope not. Yeah. Well, that's what the blocking actually does. If you find out a characteristic that you would like to block your groups on the treatment and control group, then that's what you can use. If you find out that the age or the income or something is the characteristic that they differ on, then that's what you can do. There's also in other statistical tools that are available, there's something called stratifying, but I don't think it's widely available too. It's more of a data mining process, so it's beyond that presentation. Well, like I said, we would like to find out. All right, so the model is choosing customers that are most likely to buy something, right? And then you will have both model in treatment and no treatment, right? So let's say I am a customer who is most likely to buy coffee here, right? And we did model my characteristics, and then we send me an email. Someone will send me an email saying, "Here's a coupon, buy a coffee." And there's someone else, very just like me, who is always buying coffee in the shop but does not get an email, and he will go and get that coffee anyway. So that's why you would like to know if the treatment and control group are both in the model, so you can compare if your treatment really worked, if sending an email did something or not. Okay. All right. I guess this is it then. Thank you very much.